Now let's look at the next topic, multithreading. What do you mean by multithreading? Multithreading basically means a lightweight process. Threads are lightweight processes. Threads are separate paths of execution which are functionally independent of each other. Now, how are threads different from multiprocessing or even multitasking? Because in case of multiprocessing, what happens is it is many user processes which are being processed by a single processor. Multitasking is single user many processes being processed by a single processor. So if you look at, for example, Unix system or novel NetWare systems, you have any commands that you specify goes to, in a Unix system, to the server processor, gets executed there. So if we are talking about 10 users working on a Unix system, all 10 user processes get executed in the server processor. Unix system is also multitasking. So how do you say multitask? How would you define a multitasking then? As we said, a single user, multiple processes is multitasking. As a single user of a Unix system, as one of the users of a Unix system, you can issue more than one process command. You can have one foreground command and rest background commands. So each of those processes are still executed at the server. But as a single user, you are executing more than one process. So that becomes multitasking. Similarly with your Windows platform. You open to a notepad, open to a calculator, you open to your email box. You are working with more than one application at a time, more than one process at a time. So that becomes multitasking, single user, many processes. Multithreading is single process, within that single process you have paths of execution. That is multithreading. Within a single process, you have multiple paths of execution is multithreading. For example, you open a Word document. In the Word document, you will type in the Word document, and at the same time while you are typing in, autosave gets executed parallelly. Spell checker gets executed parallelly. I mean, it looks parallel to us, right? At the same time. How is all these three things happening at the same time? Because it's multi-threaded. Sometimes you might also have noticed, you might have opened to multiple browser windows, probably by saying new window through links. If you were to close the first window that you had opened, you will see that all the rest of the windows will also get closed. You might have observed this sometime. So that's again multi-threaded. In case of multi-thread, if you were to check out your processes which are running, you'd only see one process running. For the threads, you don't see the process. So there is no process ID as such. So they are lightweight processes. If the main application were to close, the threads do not exist. Imagine closing your Word window. Will your document, spell checker and your autosave be running? No. So in case of multiprocessing and multitasking, each process has a process ID. It has its own memory space to work with. In case of multithreading, since it is a single process within which you have multiple paths of execution, for a threaded application, it is all the threads share the same resource that has been allocated for the application. So the same memory space is shared by all the threads in case of a multi-threaded program that has been allocated for the application. That's the difference between multiprocessing, multitasking and multithreading. Now threads have their own life cycle, they have their own properties. There are different types of threads that you can create. There are various ways of creating threads. Let's look at all these applications. A thread life cycle starts with the ready state. From a ready state, it moves into a running state. From a running state, it can move into a sleep state or to a death of a thread. To move from ready state to a running state, first let's understand when is it in a ready state. When you create a thread, it's in a ready state. To move from a ready state to a running state, we invoke the start method. Start method in turn calls for a run method. So then it comes into a running state. From a running state, it can go to a sleep state in 3 different ways, or a wait state, whatever you want to refer it as, in 3 different ways. That is, using sleep method, which takes milliseconds as parameter, using suspend method, or using the wait method. If we use a sleep method to put a thread into a sleep state, the thread will be in a sleep state till the specified number of milliseconds, after which it will automatically come back into a running state. If you call suspend, to bring back from a sleep state to a running state, we need to call resume. If you call wait, then you need to call notify or notify all. To move from a running state to a death of a thread, you come out of the run method, which the start has invoked, or call stop on the thread. It is the run method where the entire execution of the thread is defined. Our entire functionality of the thread is defined in the run method. So when you come out of the run method, it's the end of the thread. Since JDK 1.2, the stop, suspend, and resume methods have been deprecated. It means to say that you should no longer use these methods. You just get a warning if you were to use it. It's not an error. So you should not be making use of these methods ideally. The reason why these have been deprecated is, imagine your thread is running, one thread is running, another thread calls stop on this thread. You have thread 1, thread 2. Thread 2 calls stop on thread 1 when thread 1 is working with some resource. So it abruptly comes out of execution, leaving the resources which can damage the data or corrupt the data. So if at all you want to come out of execution, come out with the proper conditions. You should not be therefore using a stop method. That's why it's been deprecated. Similarly with suspend, if you invoke on a thread, till resume is called, you're not going to come back. So till then, you're holding the thread state. Okay, so that can end up getting into a loop, in a sense that you will never end your program totally, and other threads could end up waiting. We'll look more into why this is so little later when we discuss about synchronization. You'll understand better with that. So this is the life cycle of a thread. The wait and the notify methods we will discuss later again. In order to work with threads, we have the following classes and interfaces. We have the thread, the thread group class, and the runnable interface. All these reside in the lang package. Threads have their own properties. Every thread have property. The properties of a thread is every thread has a name, it has a priority, and it belongs to a group. So there are methods in the thread class which allow you to work with these properties, called getOrSetName, getOrSetPriority, and getThreadGroup. Till now you have not written any threaded program. You just wrote a plain application. You did not multi-thread your programs. Whatever program that you wrote was the main thread or the system thread. That was the heavyweight thread part. So even that thread has the name, priority, and the group to which it belongs. The name given to a main thread or the system thread is main, the group to which it belongs is main, and the priority is a normal priority which is given to it, that's 5. When you create a thread, you can specify the thread with its name at the time of creation. And you also specify the group to which it belongs at the time of creation of a thread. If you do not specify the name for a thread when you create a thread object, the API, the thread class, assigns the thread with the name as thread 0, thread 1, thread 2, so on and so forth. You can of course change the name of a thread by calling a setName method later on. Now for the group. The thread group has to be specified when you create an instance of a thread itself. As you notice, there is no set thread group, there is only a thread group. So you create a thread group object and specify that object of thread group when you are creating a thread object. If in case you do not specify a thread group to which a thread should belong to, then automatically the thread will get placed into the same group as its parent thread. So in the main thread, it belongs to the thread group called main, and in that main thread, if you were to create a child thread and you don't specify the group to which the child thread should belong to, it also belongs to a group called main. So if you want it to be grouped separately, create a thread group object and pass the thread group object as parameter when creating a thread object to its constructor. Why do I need to create thread group or group together threads? For example, if I want to manipulate set of threads together, that's when thread group is useful. Let's say you want to put n number of threads with all the threads within a particular group to a sleep state, you can put it to a sleep state. So you can manage the set of threads at once using a thread group. That's the reason for having thread groups. Certain functionalities can be provided commonly when you group these threads together, instead of calling them on each and every thread. The priority of a thread can be specified between 1 and 10. 1 being the minimum priority, 10 being the maximum priority. So therefore, normal priority is 5. You can set a priority for a thread, of course, by calling a setPriority method. You need to specify a value between 1 and 10. If you specify a value beyond this range, either way, you get an exception, illegal argument exception. If suppose I don't set a priority for a thread which I create, then the thread gets the priority same as its parent thread. Apart from all these properties, what else can I do with a thread? Suppose you want to have one thread waiting for another thread to complete and then continue with its action. Then you call a join on the thread. Let's say I have thread 1 which has executed certain step of information. So we have thread 1 and thread 2. Thread 1 has executed some amount of its execution or functionality, after which it would need to wait till thread 2 completes and then it should continue. Then what you need to do is, in thread 1 you ask thread 1 to wait till thread 2 completes. So you say thread 2 dot join inside of thread 1. So this goes into a join state wherein thread 1 waits till thread 2 completes. Once thread 2 dies, then thread 1 continues with its further execution. This join method throws interrupted exception. Similarly, even the sleep throws interrupted exception. Now, when does this interrupted exception occur? Whether it's for join or sleep, is that suppose, for example, whatever the thread 1 has to do after this particular join point depends on only whatever the thread 2 had to execute up till here, after which thread 1 need not wait for thread 2 to complete, assume. In that case, in thread 2 what we can do is, we know after this particular statement thread 1 can proceed with its functionality, but we have called join because join means to say once thread 2 dies then continue. So what we do here in thread 2 is call thread 1 dot interrupt. So interrupt is a method in the thread class as well. When we call an interrupt method on a thread which has called join or which has called sleep, it throws the interrupted exception and comes out of the join or the sleep state and continues further in its execution. So now thread 1 can continue as well as thread 2 can continue with its action. That's the requirement for join and interrupt methods. Threads work in two ways. Either it's a preemptive threading or it's a cooperative multithreading. In a preemptive multithreading, all threads get the chance at the CPU time. It is a time shared process. Each and every thread gets some amount of time for execution. Depending on the JVM implementation, either this could be queued or it could be randomly picked as to which thread gets to execute next. But let's say a higher priority thread comes into picture, then automatically the higher priority thread gets the CPU time first. So how does the priority make a difference? The higher the priority, higher the preference at the CPU time. So the highest priority thread gets the CPU time first, and after which the rest of the threads get their CPU time. So it could either be queued and one after the other the threads could be executing, or it could be just randomly each of the threads gets some CPU time to get executed. That is preemptive multithreading. In case of cooperative multithreading, what happens is the highest priority thread always gets a CPU time till it is done with. Then only the rest of the thread get their CPU time. That is, the next highest priority thread gets a CPU time. So it's always a selfish thread in cooperative multithreading. If in case the highest priority thread goes into a sleep state, then the next highest priority thread gets a CPU time to execute during that point of time. Once this highest priority thread which has gone into sleep state comes back into running state, again it gets the CPU time. So it always rules the CPU time. In case of cooperative multithreading, if you want to build an unselfish thread, what you can do is you can use the yield method, provided that you specify all the threads with the same priority. Again, if it is different priority, calling yield is not going to make any sense. What yield does is, it puts the current thread which is under execution, in which you are calling a yield function, to go to the end of the queue, or to give up the CPU time so that the next thread can get the execution. So if you have all the threads at the same priority level in a cooperative multithreading, each thread after some time calls yield function. It then gives up the CPU time, so some other thread gets the CPU time to execute again. And again that thread calls after some time the yield, again the next thread gets a CPU time. So you can build a unselfish thread that way. In preemptive multithreading, calling a yield method also gives up the CPU time, letting some other thread to capture the CPU time. So suppose in thread 1, if I were to call the yield method, when thread 1 is executing, maybe when I come here, let's assume the CPU time allocated for thread 1 at this point is 50 milliseconds, out of which I have elapsed 40 milliseconds and I still have 10 more milliseconds left, but I come across the yield function at that point. So although I still have 10 milliseconds left, I give up my CPU time so the next thread can get the CPU time. So that's the yield functionality. You want to find out whether a particular thread is alive or not. Is alive method returns true or false. Now remember, we are placing threads into a thread group. The thread group class has similar functionalities as a thread to operate on group of threads which belong, set of threads which belong to that particular group. Not only that, it also has active count, all the count of threads which are available in that particular thread group. And it also has a method set max priority. Now let us see how this set max priority works. Let's assume I have thread 1, thread 2, thread 3. And let's assume all these 3 threads belong to a group called TG1. I would have created thread group TG1 is equal to new thread group. And while creating these 3 threads, I have passed TG1 as a parameter. Now let's say I set the priority for T1, set priority of 9. Let's assume that then I say TG1 dot set max priority of 8. Then we say T2 dot set priority of 9 and T3 dot set priority of 6. Now if I were to, after this, display what is the priority of each one of these threads, you would find out that T1's priority is 9, whereas T2's priority is 8 and T3's priority is left at 6. The reason for this is you are setting the priority of T1 to be 9 before setting the max priority of for the group to be 8. When you set the max priority for a group, it means to say that any thread that belongs to that particular group cannot have a priority greater than 8. Although the allowed priority is between 1 and 10, you are setting any thread belonging to this particular group can only have maximum priority of 8. But this particular thread also, T1, belongs to Tg1, but its priority has been set prior to setting the max priority of the thread. So at the point when you set this priority, the max priority was 10. Okay, so if you are setting the priority of a thread after setting the max priority, and that priority which you are setting is greater than the max priority, it does not throw an exception. It just takes it as a max priority of the thread group. As long as it's within the max priority, it leaves it as it is in case of thread 3. Now after all this, if you were to reset the thread 1's priority again, at that point the max priority comes into picture, or it takes an effect. So this is how max priority works. There are two types of threads that we can create. They are user threads and daemon threads. When you create a thread object and then call start on that thread object, that thread is a user thread. When you create a thread object and before calling a start on the thread object, if you were to call set daemon of true, if you say set daemon of true, then you are creating a daemon thread. If again you create a thread object, you say set daemon of true and then call start on that thread, it becomes a daemon thread. Once you start a thread, you cannot change a daemon thread to a user thread or user thread to a daemon thread. It has to be done before getting the thread into a running state. That is before calling the start on a thread. Any thread which is a daemon thread, within which if you were to create another child thread, that also becomes a daemon thread. A child thread of a daemon thread is always a daemon thread. By default, therefore, set daemon is false. If you want to check whether a thread is a daemon thread or not, you have isDaemon, which returns true or false. Now what is the difference between a daemon thread and a user thread? Why do I need to create daemon threads? You might have heard of daemon processes. For example, Unix has daemon processes. One of the daemon processes responsible for updating the system block of the Unix environment. It updates the system block every now and then of the Unix system. Daemon processes or daemon threads are basically responsible for managing resources. For example, when I start up my JVM, inside the JVM process there is a garbage collector application running. Garbage collector is a thread and it is a daemon thread because we mentioned that garbage collector application starts when the JVM is started, and just before the JVM is shut down, the garbage collector application shuts down. So what does it do, the garbage collector? It manages memory. So daemon processes are used to manage some resource. And when I manage a resource, again and again, I execute the same set of instructions. So in case of a garbage collector, it does mark and sweep every time it executes. So therefore, there should be a loop, while true loop for daemon processes. So in a while true loop, you place the code. Because if I'm just going to have a daemon process execute something and come out, there is no point making it a daemon process. It can just be a user thread. I just execute and exit out. That's about it. Where I need to manage a resource, it has to happen the entire time my application is running, again and again. My garbage collector has the lowest most priority, that's priority 1. That's why even when we call GC method from the system class explicitly, there is no guarantee that particular instance itself it will invoke the garbage collector. Because it has the lowest priority, it needs to get its CPU time in the due time. So in the due time it will execute, not immediately. That's why we say there is no guarantee of executing even if you call GC. So you can also say now, if you want to write a while true loop and execute your, your code to manage some resource, why not do that in a user thread itself? Write a user thread, inside the user thread write a while true loop doing the same thing again and again. What difference does it make? The difference is the JVM is alive as long as the user threads are alive. So if you put in a while true loop in a user thread, which is an endless loop, you are not breaking out of the loop at any point, you will never come out of program execution. So your JVM will never exit. Your program never ends. Whereas when you put the same while true loop into a daemon process, what the JVM does is, it checks as long as all the user threads are alive, it has all the daemon threads running and the JVM is alive. Once all the user threads die, the JVM will take care of killing the daemon threads and exiting out. That is where it's going to make a difference. You are not to kill the daemon threads, it throws you an exception. The JVM will take care of killing the daemon threads. That is the difference between daemon threads and the user thread. Now that we have seen how the threads work and what properties they have, let us look at what are the different ways of creating a thread. Two ways of creating a thread. One is extending from thread class, and two, implementing runnable interface. So either you can select to extend from the thread class or implementing runnable interface. Now let us look at the steps to executing both the methods and see what is the difference between both of these methods. After that we will take a look at an example using each of these methods. Method 1, extending by the thread class. First step is extend a class from the thread class override the run method, then create an instance of the above class and start the thread. In the second method, that is implementing the runnable interface, first thing that you do is, of course, implement runnable on a class This runnable interface has only one single method, that's the run method. So implement the run method. Of the runnable interface, create an instance of the class then what you have done here is when you created an instance of a class of the above class, this class is implementing the runnable interface. So when you create an instance of the class implementing the runnable interface, what type of an object do you get? You get a runnable object. But here when you created an instance of the above class, in the first method, the class for which you are creating an instance is extending a thread class. So this instance which you are creating is nothing but a thread object. So here you just have a runnable object. You need to create a thread object. Create a thread object by passing the runnable object as parameter. So when you create a thread object, the first parameter that you need to pass is the runnable object, which is nothing but the instance that you created in step C. By passing the runnable object, you created a mapping between the thread and its runnable object. And then call start on the thread. Now let's see what's happening here. You take a class, extend from the thread class. You're overriding the run method which has been written in the thread class. The run method out here and the run method out here are the same. What the thread class is doing actually is, the thread class implements the runnable interface and it implements the run method of the runnable interface as a do nothing method. So you override that run method to give a implementation for the thread. Remember, the run method is where you give the entire implementation of the thread or the functionality of the thread. And you create an instance of the class, you get a you get a thread object here, since you are extending from thread. So on the thread object, you just invoke the start function, start method. The start method, in turn we said calls the run method, thereby getting the thread into a runnable mode. Now in this particular case, second method, you take a class implementing the runnable interface, override the run method of the runnable interface where you define the functionality of the thread. You create an instance of the class, so you get a runnable object. You still need to create a thread object and then call the start on the thread. While creating a thread object, if you do not pass the runnable object as parameter, and if you were to call start on the thread, the start will automatically call the run on the thread for the runnable upon the runnable object. Thread itself is also a runnable object. So if you are not passing any runnable object as parameter, it itself is a runnable object, so it will call run method on itself. Therefore, the run method of the thread class itself gets executed. which does what? Nothing, because it's a do nothing method. It just gets in, gets out of the method. That's why we need to provide the runnable object as a parameter here. So when the start method calls the run, it calls the run on the runnable object that you provided. Now the question would be, why should I call start method? Can I just call the run method directly? I'm overriding the run method of the thread or the runnable interface. Why should I call start and start in turn call the run method? Can I not directly call the run method myself? Instead of calling start here, I'll say call run method on the thread. There's nothing wrong. But then it's not a separate execution of thread. It's in the current thread itself, it's like calling another method, that's all, if you end up calling the run method. But if you call a start and start calls a run, the start, what it does is, it takes the thread on which you have called the start on and it schedules it with the CPU so that it gets to execute as a separate path of execution and not within the same thread where you created this particular thread object. That's why we need to call start method and not the run method directly. So these are the two methods or two ways of creating threads. Now let's take a look at an example. Let's write an example for hello world. We will use both the methodologies to create a thread. Let's say we have two threads, one thread displays hello, another thread displays world. So since there are two different messages that each thread has to display, but the functionality is same, just to display some message, okay, we'll have the same functionality being executed by two threads, but the message that it displays would be different. So we'll have class thread test, which will have public static void main of string array. Here we'll create new disp thread object. Now what is this disp thread? We have a class disp thread. Let's follow the steps that we wrote. We are going to look at the first method, extending by the thread class. First method says extend a class from the thread class. So we have a class which extends from thread. The next step says override the run method. So public void run. In this run method, all we want to do is display hello, whatever the message, right? Now where is the message coming from? Now remember, both the threads are going to execute the same run method. So if you want to have two different messages, we need to pass the message to disp thread somehow, and that is through a constructor. Let's say hello will be displayed by disp thread 1. And similarly, we will create another disp thread object, dt2 is equal to new disp thread which takes world, which means to say that I need to have a constructor here which takes a string message which I need to display here. But how do I access this local parameter out here in this method? Declare a variable here in the class to which you equate the local variable value and access the message in the run method. Let's say we put it into a for loop, for int I is some value, as long as int I is 0, I less than some value, I plus plus. In this you write the SOP to display the message. So once you have overridden the run method, we said create an instance of the class. So we created 2 instances of that class. Thereby we got 2 thread objects, because the class extends from the thread. An object of that class is nothing but a thread object. Next, call start on the thread. So dt1.start and dt2.start. Which ends up executing the run method out there. Now let's see how the execution happens. When I say Java thread test, a main thread or the system thread executes the main function, and the system thread creates an instance of this particular class. When it does so, it executes the constructor, comes back here, again creates the next instance to execute the constructor, and comes back here. Till now we still have a single thread, that's a system thread. Now we call dt1.start. The start gets called within the main thread, which creates a separate path of execution for dt1. So in that separate path of execution, the run method is called for dt1. Then dt2.start is called. So again inside the main thread, this is start is getting executed. The start again creates another path of execution within which the run method for dt2 is getting executed. And when the main thread, the next thing the main thread does is, it's done. That's the end of the main thread. Main thread has exited. But that does not mean my program execution is done, because now I have 2 user threads running still, the child threads. The child threads go into their loop to execute the loop to display the message n number of times. Once they are done, the entire program comes out of execution. This is how threading works. Now let's take a look at the second methodology. The second methodology says, take a class, implement it with the runnable interface, implement the run method, create the instance of the class. When you create the instance of a class, what type of an object do you get? You get a runnable object. You don't have a thread object. You need to create a thread object. So create the thread object. Thread T1 is equal to new thread of, pass the runnable object to it, dt1 and dt2, 2 different runnable objects, because we want to have 2 different messages for each of the threads. Call the start on the thread. This is the second methodology to execute the same program. Now what is the difference between implementing runnable and extending from the thread class? The difference is, if you wanted to extend from the thread class, it's possible only if you are not extending from any other class, because it's a single multi-level inheritance in Java. Whereas implementing an interface can be done on any class easily. Another important point is that if you extend from the thread class, the entire functionality of the thread is inherited into your class, and you can override the functionality of any of those methods of the thread to give your own definition. And you are loading the entire content into your class, the entire characteristics into your class, which becomes heavy. That's the difference. Rather than creating an instance, you are simply extending by the thread class, you are inheriting all the contents just to override the run method. That's the difference between implementing runnable versus extending the thread class. That's why implementing a runnable interface is a preferred methodology. Now that we have looked at how to create a thread, what are the different types of threads and properties of a thread, let us understand why we need to create threading or the threaded program. A threaded program is required in cases where you're going to have an animation or a client-server type of programs. But these are not the only places where you need to use threading. There are multiple other reasons for making use of threads. For example, in our event handling also, it is multi-threaded. It creates a thread, and within the thread the event handler method gets executed. So let's take a look at animation. You would have seen that a lot of animations which keep running will also let you specify certain features for that animation through a GUI, that is a graphical user interface, and depending on what values you feed in, accordingly the animation also changes. But just because when you are feeding in the data in the GUI, the animation does not stop, it keeps running on its own. Now how are both of these possible? Letting the user enter into the UI as well as the animation happening on the same application or on the same program is again multi-threaded. And you know, animation keeps occurring again and again, so it has to be in a while true loop. In case of a client-server program, you have a client machine and a server. Let's take an example. All of us connect to Yahoo server. We all say yahoo.com. How does Yahoo give a response to each one of our requests? Each request is treated as a thread at the server for each user request. So it creates a thread. Within that thread, it takes the request from the user, processes the request, writes back a response to the client. So client-server programs are multi-threaded for every client request. Let's take a look at an animated program. We're going to write an applet program which is going to display a banner just saying welcome to banner program. So let's see how to do that. We are going to have a string variable in the start method. We are going to create an instance of thread. So T is equal to new thread of the runnable object. So we are using the second methodology. So let's have this class implement runnable interface. And the runnable object is this reference. The current object which has invoked the start method is also a runnable object. You need to create a thread object only if T is null. and then start the thread. In the stop method of the thread, if t not equal to null, we will call the stop on the thread. We also need to override the paint method in which you do a drawString of s at x comma y position, let's say 10 comma 50. When you have implemented the runnable interface, you need to override the run method. So public void run. This is where the functionality of the thread is. Now what are we supposed to do? We are supposed to change the data. In animation, what happens is it goes in a while true loop because it keeps happening again and again till the application ends. Change the data, redisplay the information, wait for a while, and again go back to changing the data. So what we are going to do is, initially we will display welcome to banner program, then we will display welcome to banner program W, and then welcome to banner program V. So in other words, we keep extracting the first character of the string and add that to the end of the string. So that way it keeps rolling as if it's a circular banner. So in order to achieve this, we write this into a thread. So we have a while true loop. We need a character variable because we are going to extract the first character and store it into a character variable, put it into a string. So we say ch is equal to s dot, to extract the first character, char at 0. You get the first character into ch. Now what you do is s is equal to s dot substring from the second character till the end of the string. So that is 1 comma s dot length. You extract and put it back into s. So what s now has is elcome to banner program. Now the extracted first character is in the ch variable. Add that to the string. So s plus is equal to ch. So you get elcome to banner program W inside the string s. You need to redisplay this string, so call a repaint method. Put the thread to a sleep state. For a few milliseconds. Remember, the sleep method throws interrupted exception. End the loop, end the run function and the class. So what's happening here is a thread gets into a while true loop, keeps extracting the first character, extracts the second character till the string, puts it into a string, attaches the first character to the end of the string. When the repaint is called, the repaint is a method in the component class which we have inherited via applet. The repaint, what it does is, it schedules the update method to be called. Update is another method in the component class which also takes a graphics object as parameter. So paint, repaint and update are methods of the component class. When you call a repaint, it's going to repaint the entire size of an applet. So that is, it's going to schedule the update to be called, and when the update is called, the update in turn calls your paint method. The paint method is going to draw the string again. So when you call repaint, finally the paint will be called to display the value of s, and the value of s has changed due to your change of data out here. So that's how you get a change of information on the screen. If you want, you can specify repaint of so many milliseconds, which means to say within the specified milliseconds the update has to be called. Suppose, let's say you have called a repaint method, repaint has scheduled the update to be called. By the time update is called, again the repaint has been called. What the repaint does is, it doesn't bother scheduling the update again, because already scheduled update method has not been executed. So it doesn't bother creating another update method. So whatever scheduled update method, when it gets executed, it will display the change of information. You can also specify to repaint only certain portion of your UI. Now here we said we are repainting the entire applet, because how do I know it's an applet? Because you're calling repaint, when you call just the repaint, it's like saying this dot repaint, and what is that this? It's nothing but an applet. So you can specify to the repaint method x, y, width, height, so that only that rectangular area can be repainted instead of the whole applet. So why can't I just call the paint straight away? Because what repaint does is, it goes to the entire hierarchy of the object on which you are calling the repaint, the entire tree of that object, and calls update on each one of them. So that's why we should not be calling directly the paint method from here. So this is how you write an animated program. Now that we have seen how to write a multi-threaded program, let us see what are the troubles that we face with a multi-threaded program. Now when I have a multi-threaded program, since all the threads share the same memory resource, so whatever information that I have stored is also shared by all these threads. And when I have a shared data between threads, and all the threads manipulate on the shared data, finally the information might be wrong. For example, let's say a railway reservation counter. We all go to a railway station. We want to book for certain number of seats. So what we do, let's say one person goes to one counter and another person goes to another counter to book for tickets for the seats on the same train. So when they go to book the seats, what does the counter do first? It finds out how many seats are available, and then they let you know whether seats are available or not. Depending on that, they book. So when both the counters request for the seat availability, do they request into their own machine? You mean to say the data will be available in each and every counter's machine? Doesn't make sense, right? It will be available in one centralized area, in one centralized machine. So for this centralized data, okay, these two counters are threads. This centralized data is being shared by these two counters, and when both these counters request for the seat availability, they both contact this common data and get the seat availability. Let's assume 10 seats are available, so they both get 10 as a value. Now one person who has come to counter 1 says I want 3 seats, counter 2 the person says I want 2 seats. So finally how many seats should be available at the end of the entire transaction? 5. But now what could happen is, remember both have inquired how many seats are available, so they both end up getting 10. One counter updates by subtracting 3, another counter updates by subtracting 2, and they both say update. When they update, this counter says update to 8 and this 7, and this counter says update to 8. Finally the updation could either be The seat availability could either be 7 or 8, or it could also be 5, but there is no guarantee that it's going to be 5, right? So it has to be 5 actually, but there is no guarantee on this, because both threads are accessing the common information at the same time. So what you need to do is, you need to make sure such common information being accessed by multiple threads should be done one at a time. So one counter enquires and transaction ends, then only the next counter should enquire and end the transaction. So that at any point, only one thread manipulates the information, and once it is done, the next thread manipulates. So I am guaranteed that the data or the information is correct. So in order to achieve this, we use what is known as synchronization. Synchronization is nothing but placing a lock on an object, so that only the thread which has placed a lock can access that particular information, and once it is done, it releases the lock so that the next thread can access it. To work with synchronization, you use the modifier called synchronized. Synchronized modifier can be used against a method or as a block. Again, I repeat, synchronized is used to place a lock on an object. On a object. This is very important. Okay, the lock is placed on an object. It's an object lock. So let's see how to write this. So you say synchronized against a method, or you can have synchronized as a block inside the method. Either one of these situations. What is the difference? Now, the difference is, a method is written inside a class. So, in order to access this method, you are going to create an instance. Using an instance, when you invoke a method which is synchronized, the object which is used to call the method is the one which gets locked. So if this is in class A, I have a method, synchronized method M in class A, let's assume. I create an instance of class A called A1, and using A1, let's take this, let's say class A, I have synchronized void M. In order to access this method, we create an instance of A. Using A1, we invoke the method M in some thread. Let's call it as thread 1. Thread 1 calls A1.M. Since M is a synchronized method and M is called through A1, now you have object A1, right? This object has many instance members, plus it has a pointer to the method table, okay, and also it has a placement for lock. So when I call A1.M, since M is a synchronized method, thread 1 is calling M, so thread 1 places a lock on object A1. So when it says it's placing a lock, now here the information in the lock changes. Now it will be either 1 or 0, 1 for locked, 0 for not locked. So it changes to a lock. So it places a lock on this object A1, because that's the object I used to call this synchronized method. When does this memory space for lock get created? Now it really depends on the JVM implementation. The JVM can allocate a memory space for the lock of an object either at the time of creation of an object or the very first time using that object I call upon any synchronized area. Either one of these cases. It really depends on the JVM. So anyway, I have a placement for lock which gets converted from 0 to 1 or 1 back to 0. So I place a lock on object A1. Once I complete this method, I come out of the method M out here, then this lock is released by converting back to 0. Now let's say if thread 2 was also trying to call the same M using this object A1, now what happens is, since T1 had already placed a lock and was inside the synchronized method, T2, which has tried to call M, cannot get into the method M because T2 also requires to place a lock, but the lock was already placed, so he cannot place a lock again over it. It has to wait till T1 completes the execution of M and then releases a lock, and when the CPU time is given for T2, then it places a lock on A1 and then goes into the method. So at any point only one thread can access a synchronized area by placing a lock on an object. Now, how is this synchronized against a method different from synchronized as a block? Now let's assume instead of synchronized being specified here against a method, I specify it as a block inside here. Now in this case what happens is, synchronized as a block, since the object that you have to pass as a parameter here to this block, okay, it can be any object. If it is the current object itself, the same class object itself that you want to lock, you can just say this. If it is any other object actually which you require to lock and not the current object, then it is, synchronized block is very useful. Assume the thread is calling M, method M, but it is not A1 that has to be locked, rather some other object which has to be locked, then better to use the synchronized block rather than synchronized at the method, because synchronized at the method will always lock the current object. So if it is not the current object that has to be locked, rather it's some other object, it is always better to use synchronized block. Moreover, let's assume if you were to say synchronized against a method, till I complete the entire method, the lock is placed. Till then the other threads have to wait. Maybe the entire execution of this method is not critical. Only portion of it is critical. So then locking for the entire period doesn't make sense because you are just holding the resources. Remember, the reason for multithreading is better CPU usage, to make use of the CPU time in a better way. Because what happens is, especially in I/O operations, there is a lot of polling that's done. So during that time, CPU time is being wasted, just it's idle. So during that time, you can probably execute something which is independent of this particular task. That's the reason for multithreading. So if you unnecessarily lock for the entire period of time, you are wasting the CPU time. The whole idea of threading is lost. So if you don't require that the entire method execution period, the object be locked, then again synchronized as a block is ideal to be used. So assuming that only this portion of the execution is critical for an object, okay, you can make this as a synchronized block, and these other instructions can get executed without having a lock on an object, so that other threads can get in and start their execution. And the lock would be therefore be placed for a very small amount of period. So that's a difference between writing synchronized against a method versus as a block. Now let's take a look at some of the scenarios, how it works with a lock. Let's assume I have class A which has synchronized void F1 synchronized void F2. Let's assume I have these two functions in a class A, two synchronized functions. Let's say I have thread 1 and thread 2. I have object A1 for class A, which both the threads can access. Remember, the lock is on the object. Keeping this in mind, think about all the different scenarios that we're going to come across. So let's assume that T1 calls method F1 and T2 calls method F1 as well. By now we know that if T1 is calling method F1 using object A1, let's assume T1 calls F1 first, so it has placed a lock here. Now T2 were to call A1.F1, it also requires to place a lock here, but there is already a lock, so it cannot place, it has to wait at that point. Once F1 is done with and it releases the lock, making it 0 again, then only T2 can call F1 by placing a lock again. Now let's assume T1 calls F1 but T2 calls F2. Now the question is, would they both be able to execute simultaneously? Let's see whether your thoughts were correct. Because see, T1, when assuming that T1 calls F1 first, it places a lock on this A1 object, because synchronized first of all is against a method on both. So it's the current object itself that gets locked. So T1 has placed a lock on this object A1. Although T2 is calling F2, but it's the same object that it is using to call F2, which is also a synchronized method, which means for any synchronized method I need to place a lock. So it needs to try to place a lock here, but it cannot because there is already a lock, so it has to wait at this point. So although there are two different methods, since both are synchronized methods and it requires a lock to be placed in order to get into a synchronized method, it will not be able to invoke it. So it has to wait till the lock is released. Let's assume I just have void method 1. Which is non-synchronized. Assume that thread T2 wants to call method 1. Can T2 call method 1 simultaneously when F1 is called using thread 1? Now let's assume T1 has called F1 first by placing a lock because F1 is synchronized. Now T2 gets a CPU time and it wants to call M1. Can it call M1? M1 is a non-synchronized. So does T2 require to place a lock on the object when it's not a synchronized method? No. Only if it is a synchronized method, the thread requires to apply a lock on an object. If it is not a synchronized method, I just can get in and execute the method. So since M1 is not a synchronized method, thread 2 will be able to execute M1, although thread 1 has placed a lock on an object for the period of the synchronized method. Now let's assume I have object A1 for thread 1 and object A2 for thread 2. And using A2, thread 2 wants to access F2 or even F1, doesn't matter, both are synchronized methods. So now if thread 1 has already called F1, which is a synchronized method, placed a lock on A1's lock, can thread 2 call F2 on A2? Although both are synchronized methods. Now let's see. Remember, A2 is having its own memory map. There is a lock for A2 also. Can thread 2 place lock on A2? Although both are instances of the same class, both are calling synchronized methods? Yes, it can, because A1 object is different, the data in A1 is different, the data in A2 is different. They are two different objects that they are working on. So they are two different independent locks. So yes, T2 can place a lock on A2 and call F2 when T1 has placed a lock on A1 and called F1. Because the data is not shared, there are two different data for each of the threads. So they are able to call. Synchronization can be nested. Within a synchronized method, I can have a synchronized block for some other object also, or for the same object. Or within a synchronized method, I can call another synchronized method. When I call one synchronized method from within another synchronized method by the same thread, it is okay. But let's assume I have called F1 and F1 through T1, thread 1 calls F1. Let's assume thread 2, let's assume that thread 2 calls A1.m, which is a non-synchronized method. From here, let's assume that I call F2, which is a synchronized method. Now, at the point when I need to call this F2, since it's synchronized, at this point the thread 2 tries to access a lock on the current object, that is this dot F2. But it will not be able to access because thread 1 has placed a lock. Right? Now, but in case, let's say from F1 I might be calling M1. Now T1 has called F1, placed a lock while calling F1. F1 calls M1. M1 in turn might be calling F2, which is also synchronized. So there are two levels of synchronization I have gone through for the same thread. It doesn't require to acquire a lock again. It just keeps account of how many synchronized areas I have nested through. So that many synchronized I need to exit out of in order to unlock this. So I can have nested synchronization for a thread. But only thing is I need to come out of that many synchronized blocks in order to release the lock. Can I place a lock on a static method? Remember, the locks are placed on an object. So can I specify synchronized for a static method? Answer is yes, you can. So if you can, and you're going to access static methods using a class name, so what is the object on which you're going to place a lock? Right? Because for instance methods, you're going to use an instance to invoke the method, and the instance that you used is the one which gets locked. For static methods, which object gets locked? The object that gets locked in case static methods are synchronized is the class object. Which class object? Remember, for every class, there is an instance of class created by the JVM. That class object gets locked. So if suppose I have synchronized void S1 void S2 static and let's say I just have a static method which is non-synchronized. Let's call this as SS1 and this one is S1. Let's see how this entire thing works. Let's assume that thread 1 calls SS1 and thread 2 calls SS2. Is this possible? Please note, when we are calling SS1, SS1 is a static synchronized method. So we have a class object for A, let's call it as CA. This also has a placement for lock. So when thread 1 calls SS1, I place a lock on the class object of class A. So when thread 2 calls SS2, using any object, let it be A1, let it be A2 or A10, does not matter. It would not be able to place a lock on the class object, so it has to wait. Now if I call S1 here in thread 2, which is a non-synchronized static method, then yes, it can invoke it because it does not require to acquire a lock for it, as it is not a synchronized method. Now let's assume that I have T2 which wants to call F1. Is this possible? T1 has called SS1, which is a static synchronized method, whereas T2 has called F1, which is a instance method. Now in case of a static synchronized method, the lock is on a class object, but whereas in case of an instance method, the lock is on the instance itself, that is on A1 itself in this case. So yes, both the threads would be able to execute because both would be able to place a lock or acquire a lock, because they are two different objects. One is a static method, one is a non-static method. So locks are on different objects. So yes, they can access. This is how synchronization works. Now with synchronization also there are problems. Now what are the problems with synchronization? Synchronization, by applying synchronization, I can end up with deadlocks. For example, let's say I have class A which has function 1 and function 2 which are synchronized. Similarly, I have class B which has synchronized function 3 and synchronized function 4. Let's assume that I have thread 1 and thread 2 both have access to A1 and B1, which are objects of A and B. So T1 calls A1 dot F1 and T2 calls B1 dot F3. Since they are all synchronized methods, object A1 lock has been placed by thread 1 and object B1 lock has been placed by thread 2. Now let's assume that F1 is trying to call B1 dot F4, assuming I have an access to B1 here. Similarly, I have an access to A1 here, so F3 calls A1 dot F2. Now if T1 has called F1 and T2 has called F3, already the lock has been placed on both the objects, and here inside F1, okay, it is trying to place a lock on B1 so it can call F4, but at the same time F3 is trying to place a lock on A1 to call F2. but both will not be able to call each other because already there is a lock and they both end up hanging, waiting for each of them to release a lock. This is a deadlock situation. Another famous example for a deadlock situation is a consumer-producer example. Consumer and producer both are threads. You have a stock where consumer and the producer makes use of the same stock object. Stock has quantity on hand and reorder level. Producer keeps producing, wants to produce some product, whereas consumer wants to consume the product. Now these methods are available in the stock class. Producer keeps producing, consumer keeps consuming the product, whether if it is there or not. So you need to put certain checks for these particular accesses. And both of them are working on the same stock object, same quantity on hand. So you need to synchronize as well. Now let's say a consumer has called a synchronized get quantity on get product where quantity on hand is being used. So you lock the stock object. Similarly, producer needs to call a synchronized method which is a set product. Now if the consumer has come into the get product by placing a lock on the stock object and he finds out that he does not have enough quantity on hand to consume, he needs to wait till the producer produces, then only he can consume. But the producer cannot produce because there is already a lock on an object. Now the consumer keeps waiting for the producer to produce, but the producer cannot produce because there is a lock, again a deadlock situation. Now let's see how to solve this. Let's say we have class stock with reorder level and quantity on hand. Let's say we have synchronized void get quantity on hand and set quantity on hand. This is the stock class. Let's assume that we have class producer which extends thread and producer has an access to the stock object and overrides the public void run method and using this stock object in the run method he calls set quantity on hand. While a consumer extends thread, it's also a thread class which also has a stock object, the same stock object shared by both producer and consumer. Now let's assume the consumer thread got the CPU time and he called the get quantity on hand. Now on the stock object, the lock has been placed by the consumer thread. Now once I'm in here, I need to check before let's say here we specify how much we want to consume. Once we check the quantity required is greater than quantity on hand, we cannot consume it. We have to wait till the producer produces. So I need to release the lock so that the producer can get the lock and produce, and then tell me that he has produced so I can acquire the quantity on hand. How do I do this? In order to release the lock so that any other thread can access the lock in such deadlock situations, we invoke the wait method. This is where the wait method comes into picture. If quantity required is greater than quantity on hand, we call wait. Now what exactly does the wait method do? It puts the thread, the consumer thread, into a wait pool by releasing the lock on the object. So it releases the lock and goes to the wait pool. So now the producer thread can access a lock to call set quantity on hand, produce the quantity on hand required, whatever it is, and then it calls notify. When it calls notify, it wakes up the thread which has gone to a wait state, that's the consumer thread. Once it releases the lock and comes out, now this consumer thread which was in a waiting pool, which has been brought back into a running state via notify, gets the lock again to get the quantity on hand. So quantity on hand minus quantity required. So this is where wait and notify is very useful, or different from your sleep or suspend methods. If you call suspend, we said we need to call resume. We said these methods have been deprecated. Why? Because if I call suspend, I go into a sleep state holding the lock, so no other thread can access the method also till a resume is called. Whereas in case of wait and notify, these, in order, if I have called wait, I have to call notify also. Now you can say it's the same case as suspend and resume. If I don't call notify at all, but I'm not holding a lock on an object, I've released the lock and then gone to a wait state till notify is called. But then I also have an option with the wait, that is, I can specify how long it can be in a waiting period in the wait pool by specifying wait of milliseconds. So in which case, either the thread will be in the wait pool till the specified amount of time or till the notify is called, whichever one comes first. So the same case has to occur with another thing with the deadlock here is, let's assume that the consumer thread which had placed a lock and found out that the quantity required is greater than quantity on hand, called the wait method, goes into a wait pool. By the time the producer could come in to set quantity on hand, you have another consumer thread which calls the get quantity on hand. So places a lock, comes in and checks whether the quantity required is greater than quantity on hand. It also calls wait. So now you have more than one thread in the wait pool. Now when the producer gets to lock and call the set quantity on hand, and he calls notify, which thread will he notify? Because there is more than one thread in the wait pool. The thread that it notifies depends on the implementation of the JVM. You can't really say which thread actually gets notified. It could be the first thread, it could be the last thread which went into the wait pool, or it could be the highest priority thread. Most often the JVM implements it as the first thread which goes into the wait pool is the first one to be notified. Why? Because if assume that I notify the last thread which got into the pool, the first thread might end up waiting for a long period. The same case might happen with the highest priority thread also. So therefore general implementation would be the first thread which goes into the wait pool gets notified first. Again, in general, to answer this question, which thread gets notified, you are not sure. It depends on the JVM implementation. There is a notify all method as well. Instead of calling notify, we can call notify all. In case notify all is called and multiple threads are in a wait pool, what happens is all the threads are notified, so all of them come back into a running state. So which one gets the lock first? It's the highest priority thread that gets a lock in case of notify all. So that's about the wait and notify and the notify all methods. Now one more point is that wait and notify all methods must be invoked in a monitored area. Otherwise we get illegal monitor exception, which means to say these methods must be called within the synchronized blocks, or if you were to call these methods in a non-synchronized area, the non-synchronized area must always be called through a synchronized area. Otherwise we get an exception. That's another important point. Wait and notify should always be invoked within a monitored area. So this is the difference between wait versus sleep or suspend. Again, sleep method also goes into a sleep state by holding a lock. It's only the wait method which releases the lock and goes into a sleep state. So this is how you take care of deadlock situations during synchronization process. Now this is not all of threading. There is a little more. Till now we spoke about threads sharing a common information or data. Now we will talk about where you have multiple threads. A thread has a local data or local information which is required to be passed to another thread. Now of course you can say you can put it into a class or you can pass it, but how will you pass it? Within the run method, I have some information which I have processed which I would like to pass to another thread. If you put it as a shared common information, then it's shared. What we are saying is it's a very much a local information which I need to, some data which I have generated which I need to pass to another thread. In order to pass across threads information, we talk about inter-thread communication. And inter-thread communication is always via pipes. So this is where we make use of piped input stream output stream class or the pipe reader writer class we said that we would be discussing during multithreading. So let's take a look at an example where we are going to create two threads. One is called as a running average thread, another is called as a number generator thread. The number generator thread is going to generate random numbers which has to be passed to a running average thread, which is going to calculate the average of all the numbers it keeps receiving from a number generator thread and keep displaying to the console. Let's see how to achieve this. Let's say we have class number generator extends thread, and we have class running average extends thread. Both are thread classes. Now the thing is, the number generator is going to generate a local data which has to be written to a pipe which the running average needs to read from the pipe input stream and process it. So number generator writes the data, running average needs to read the data coming from number generator. So number generator requires a pipe output stream, running average requires a pipe input stream to read from the pipe. Now pipe output stream and pipe input stream, they are two separate objects. So if I were to create a pipe output stream here and pipe input stream here, how do I connect with both? Because they are two different objects. Because what we need to say is whatever is coming from this output stream needs to be read from this input stream. There should be some way of binding both pipe output stream and pipe input stream. So because of this, you cannot create the pipe output stream here and pipe input stream objects in this respective classes. You need to create the pipe stream objects therefore here and pass the appropriate pipe stream objects to the number generator and the running average class. So we create the pipe output stream Remember, when you are working with streams, they throw exceptions, so put it in a try-catch block. Then create your piped input stream. Now to bind between the pipe output stream and the piped input stream, when you are creating this pipe input stream, pass the pipe output stream object as a parameter. By the way, you can do a vice versa also. You can create pipe input stream first, then create a pipe output stream, and while creating a pipe output stream, pass the pipe input stream object. Does not matter which way you do it. But one point that you need to remember is, once one piped input stream and one pipe output stream are mapped to each other, they cannot be mapped to another pipe input or the pipe output stream. In other words, I cannot create another pipe input stream, let's say 2, with pipe input stream passing the same pipe output stream, because I get an exception, already bound exception. So one pipe input stream can be bound to only one pipe output stream and vice versa. So once we have mapped the output stream and the input stream together, now we can create an instance of those classes. Number gen ng is equal to new number gen. Now number generator class needs to make use of pipe output stream, so it can write into the pipe. So pass that as a parameter here. And running average needs the pipe input stream. Call start on both the threads. That's class pipe test. Now let's look at number generator. We need a constructor here which takes the piped output stream object. Now the type of random number that we are going to generate here is going to be a double type, and we would like to write a double value into a pipe, and on the other side we would like to read it as a double value. So to read and write as a double data type, we need to make use of the data input output stream class. So we are going to declare a data output stream DOS is new data output stream. Again, remember, data output stream cannot stand by itself. It needs to know where to read the double from, and that is sorry, to write the double to in this case. So we need to pass the pipe output stream object as parameter. We need to override the run method. It is in the run method where we generate the random number. So we'll have random. Random is a class in the util package, so you need to import java.util here. Ran is equal to new random double D. We'll have a while true loop, which means to say we are never going to exit out of this program execution because of the way we are writing the code here. So in the while true loop, we go on generating the number, and there we keep receiving the number to keep displaying the average. So D is equal to ran dot next float is a method there. This returns a float type of value. I'm just going to apply some formula on this to get a double number. Write this double value to the pipe by saying dos.write double of D, then call flush, so to push out the contents, and then go back, generate the next number, write. This goes on happening out here. So catch exception. In case of a random running average, we need the data input stream object This takes a piped input stream object as parameter. Here we create a data input stream object. By passing the pipe input stream object as parameter. Then we have public void run. So double total, because we need to find out the average of all the numbers that we are getting. We need a counter. In the while true loop, keep receiving the value from the stream and calculate the average and display. So we take the data input stream object, call the read double method, put it into a total, increment the counter, then display the average. So this is how the pipe stream works. Now, regardless of however many numbers this particular number generator might be writing to the pipe, I would be able to receive all the values one by one to the running average and be able to calculate the average and display. So I don't lose out any data, even if this is running faster than this. This is inter-thread communication using pipes. Of course, you can use pipe reader and writer also instead of input stream, output stream. And that's about multi-threading.